So there was a question on how the Reynolds transport theorem and its combination with the Gauss divergence theorem could be applied to situations in which we need to worry about vector and tensor fields. So it does apply. They both do apply. And let me try and set up an example here to show us what goes on. So, okay, so I'm going to title this as the combination of Reynolds transport and Gauss's divergence theorems for vectors or tensors. Okay, I apologize that it's such a mouthful, but I wanted to capture all the important aspects here. Okay, so let's suppose that we are working now with the following quantity. Let's suppose that we have some, okay, so we have our basis, okay, and we are now worrying about some spatially defined vector field, and let me just draw that here. Let's suppose that we have this field u, which is a spatially defined field, u of x comma t. Okay, what could an example of this be? Probably the most convenient example to use here is when u is some sort of a magnetic force field. Okay, it works for other cases too, but this probably is the simplest without throwing up more questions. Okay, so let's suppose that, okay, so example, u x comma t belonging to R3 is a magnetic force field. Okay, and then of course the question we want to ask is, all right, how do we think of this quantity? d dt integral over omega t u d little v. Okay, so we want to integrate, so maybe it's a magnetic force field per unit volume. Okay, magnetic force field density. Okay, something like that. All right, we want to know what this quantity is. Essentially what Reynolds transport theorem and the Gauss divergence theorem applied together tell us is that this is integral over omega t. Okay, the first term is just the standard partial time derivative of u, right? It says, well, if you want to know how this is varying, just look at your region in space and freeze it at a time t, and look at how u is actually fluctuating with respect to time over that field. Okay, so this is this, and then the next term is, it tells us that, well, you also need to integrate over the boundary of your configuration at that instant. Okay, now the quantity we have is u tensor v okay, dotted with the unit outward normal dA. Okay, so what's happening is that we have our domain omega t. Okay, so in order to know how the total magnetic force field is varying, right, over some region in space, what we need to do is integrate that density over the volume, and then also account for how this particular quantity integrates up over the surface. Okay, the way where that comes from is it comes from the fact that Reynolds transport theorem on its own tells us that the integral over omega t u d little v equals integral over omega t, the partial time derivative, which stays just the same in the line above, plus the divergence of this quantity u tensor spatial velocity. Okay? This is a result we derived earlier in the segment. What is happening now is that, so this is what we get from Reynolds transport theorem. Okay? Gauss divergence theorem takes us from here to here. All right? Okay, so it's essentially the divergence of that of this tensor quantity. Okay, that's involved in the volume integral, and Gauss theorem tells us that it is, well, you just take that tensor quantity, dot it with the, or well, it's a tensor, so have it act upon our unit outward normal n, and this is the quantity we get. And just recognizing the sort of notation we're following, I don't need a dot there, right? Because u tensor v is a tensor just acting upon n. So what this is doing now is telling us that as this body tumbles through space and as the configuration changes a little, right, at the next instant time, at the next instant in time, okay, so this is omega t and this is omega, so maybe I should call this omega sub t1, and now this is omega sub t2, okay. The extra bit that you got in addition to the time, in addition to the purely time derivative, the pure partial time derivative, is this term here where, and we know that u tensor v, the whole thing acting on n, basically goes to integral over partial of omega t u times v dot n. Okay, that's simply the action of the tensor product of vectors on another vector, right? So what it is telling us is that now, over the boundary of the body omega t, you just account for v dot n, and remember v dot n tells us how the surface is moving at a particular point, right? Okay, as the surface moves, it is essentially sweeping up more of this magnetic force field density. Okay, and essentially the Gauss divergence theorem gives us a clear way of going from this term here, involving the divergence over the volume, to this final form here, involving a surface integral.